Next, we're going to talk about Newton's third law, and I'm sad to say there's actually only three of them, so this is going to be the last installment, but trust me, there's plenty of stuff that we can do with these three laws combined. So, for a quick recap of Newton's three laws, the first law says that anything that's moving or anything that's sitting wants to keep doing exactly what it's doing. The only way that you can accelerate an object, the only way you can change its velocity, is by applying an unbalanced force. And in physics, we call that a net force when the forces are unbalanced. Once you have a solid understanding of the first law, the second law is actually very simple. When there is an unbalanced force applied to the object, then you can figure out its acceleration depending on its mass. So just F net equals ma. It's the third law that everybody messes up on because that one is the most tricky. Newton's third law says that all forces come in equal pairs because a force is an interaction between two objects. You can't have an object exert a force on itself. It must come from another object. Now this might sound really weird, but if you think of it as a force being an interaction, then the interactions that you have in your life involve two different things. It's give and take. You can't give your friend $5 without you losing $5. Anytime there's an interaction, it affects both parties, and it's the same with forces. So if I push you, you push me. I can't poke you in the eye with my finger without your eye poking my finger. In fact, a joke I always make in class is if I were to take one of the students in my class and just punch him in the face, and the student went to the principal and said, "Look at my black eye, my teacher punched me." Well, couldn't I go to the principal and say, "Look at my bruised hand, his face hit my hand"? So it's an interaction between two things. So let me give you a pair of bodies to help you kind of see this. So right here we've got the Earth and the Sun, and as you know, there's a gravitational attraction between them. In fact, I'm going to draw that. Now, according to Newton's third law, there's a gravitational attraction between them, and the two forces are equal. The Earth has a gravitational force from the Sun, so we would call that the force of the Sun on the Earth. And the Sun, likewise, has a force of the Earth on the Sun. But this begs a big question, because the Earth ends up doing this crazy huge orbit where it's like the Sun is kind of whipping it around in circles, and the Sun remains relatively stationary. So how could you say that those two forces are equal? Here's the reason, and here's why people get it mixed up all the time. Yes, the forces are equal between the Sun and the Earth. It's an interaction between the two. What's different is the effect of those forces. The Sun has a lot more mass than the Earth does. So for the Earth, when it gets this force, it ends up with a small mass and a huge acceleration. But for the Sun, since it has a huge mass, it gets a very small acceleration. But that doesn't change the fact that F1 is equal to F2. The two forces are equal, but the effects of those forces are what's different. Now, there's an important mistake that I see all the time that I want to save you from. A quicker way of saying this is if you have a force from object A on object B, it's always going to be equal to the force of object B on object A. Anytime you flip these two around, that's where Newton's third law applies. But don't put it in places where it doesn't belong. Take a look at the bottom here. I've got a block sitting on a table. Now, if I were to draw a force diagram on this block, you would have a downward force of gravity and an upward normal force. So that's Newton's third law, right? You've got two equal and opposite forces? No. These are the two forces that are on the block. If you want to find the third law interaction, the third law forces, you have to find the object that the block is actually interacting with. To find the forces coming from Newton's third law, you have to ask yourself, what is the block actually interacting with? In this case, the force of gravity comes from the Earth pulling on the block, not the table. So if the Earth pulls down on the block pulls up on the Earth. This is where Newton's third law comes into play, not on the force diagram. And likewise, the table pushes up on the block, so the block pushes down on the table. In summary, make sure that you always know that on a force diagram, you will never demonstrate Newton's third law with just a single force diagram. Because if Newton's third law is about an interaction between two objects, then you would need two force diagrams at least to demonstrate it. I would have to draw a force diagram on the Earth to show the reaction force to the block being pulled on, or I would need to draw a force diagram of the table. I cannot demonstrate Newton's third law drawing just a single force diagram. You have to look at the objects from which those forces are coming.